All right, let's talk about black holes. Now, most of us probably picture these cosmic vacuum cleaners, right? Just giant objects out there sucking everything up. But what if they aren't objects at all? What if they're places? Places where the very fabric of reality, space and time itself, is stretched, twisted, and pushed to its absolute breaking point. So, come on, let's take a trip to one of these places, a place where reality bends to its will.
And asking that question, well, that's what kicks off a journey that completely flips our whole understanding of the universe on its head. And it all starts with the one thing we think we know inside and out: gravity.
Yep, you heard that right. The very first step to really getting what a black hole is to kind of forget what you learned in high school physics, because Einstein came along with this idea that was just truly radical. Gravity isn't some mysterious pull, it's the actual shape of the universe.
Okay, so think of it this way. For centuries, we had Newton's idea, right? Gravity was like this invisible rope, instantly pulling the Earth around the sun. But Einstein? Wow. He completely reimagined the whole thing. He said, no, the sun's massive weight creates this deep curve, a dent in the fabric of the universe. And the Earth? Well, it's just rolling along the edge of that curve. So that pull we feel, it's really a bend.
And this fabric he was talking about, that's what we call spacetime. Imagine a big, stretched-out rubber sheet. You put a bowling ball, that's our sun, right in the middle. What happens? It creates a dip, a curve. Now, if you roll a marble, that's our Earth, nearby, it's not going to go in a straight line, is it? It's going to follow that curve around the bowling ball. That is gravity. It's this beautiful, elegant cosmic dance where mass tells spacetime how to bend, and that bend tells matter how to move.
Okay, so if a star, like our sun, just makes a nice, gentle dimple in that rubber sheet, what happens when you have something so massive, so incredibly dense, that it doesn't just make a dimple, it punches a hole right through the thing? Well, that is when you get a black hole, the ultimate, most extreme warp in space-time you can possibly imagine.
And you better believe they are born in the most unbelievable violence. We're talking about a truly gigantic star, way bigger than our sun, that runs out of fuel. Its core just can't fight against its own crushing weight anymore, and the whole thing catastrophically implodes. There's literally no force in the universe strong enough to stop it. It just keeps collapsing, crushing all of that matter down into an infinitely small, infinitely dense point.
And that point, that's what we call the singularity. It's a place where, honestly, our laws of physics just completely break down. It's not just a lot of stuff in a small space. Try to imagine an infinite amount of matter squeezed into zero space. Yeah, I know. It's the bottomless pit in our rubber sheet, where the curve just goes to infinity. And so does our understanding, frankly.
So wrapped around this impossible point is its most famous feature, the event horizon. Now, this isn't a physical wall or anything you could touch. Think of it more as a threshold. It's the exact line where that gravitational curve gets so steep that, to get out, you'd have to go faster than the speed of light. And since nothing can do that, well, that's why it's the ultimate point of no return.
All right, so let's gear up. Imagine we're on a spaceship heading towards one of these things. As we get closer and closer to that event horizon, the very first thing we'd notice isn't the pull. It's that reality itself starts to get weird. And the first thing to go is time.
This gets to the absolute core of what's called gravitational time dilation. The simple idea is this. The stronger the gravity, the deeper that curve in spacetime, the slower time actually flows. And hey, this isn't just sci-fi theory. Our own GPS satellites right now have to constantly correct for this tiny little effect every single day, just so your maps work. But near a black hole, this effect goes from tiny to absolutely mind-blowing.
So let's really play this out. Imagine you're the astronaut falling in. From your point of view, everything seems pretty normal. Your watch is ticking away just fine, and you cross that event horizon in, a reasonable amount of time. But for me, watching you from my spaceship a safe distance away, I'd see something totally different, something incredible. I'd watch your clock appear to slow down, slower and slower, until right as you hit the edge of the horizon, it would look like it just stopped. From where I'm sitting, you'd be frozen in time, at that boundary, forever.
So, while time is stretching out like taffy, space itself is bending. A black hole's gravity isn't just pulling on things like our ship, it's bending the very path that light takes, turning all the space around it into this giant cosmic lens.
You see, light always tries to travel in a straight line, but when space-time itself is curved, what even is a straight line anymore? The path gets bent right along with the space it's traveling through.
So light from a star way off in the distance that passes near a black hole gets warped. This can create these distorted, magnified, sometimes even multiple images of the same star. It's like the universe's ultimate funhouse mirror.
And listen, this is not just some cool theory we cooked up. In 2019, the Event Horizon Telescope gave us the proof, the actual receipt. This picture, this is the first ever direct image of a black hole's silhouette. That dark circle in the middle, that's not the black hole itself, that's its shadow, cast against this incredible, glowing, superheated gas that's swirling all around it. And that brilliant, fiery ring, that's the light from the gas, being twisted and bent around the event horizon by gravity. We are literally looking at a photograph of warped space-time. How cool is that?
Okay, deep breath. We've seen time grind to a halt. We've seen space bend like a lens. Now, let's do it. Let's take that final, fateful step and cross the boundary. What in the world happens inside the event horizon where all the rules we thought we knew get completely thrown out the window?
The second you cross that threshold, something fundamental, something profound happens. Space and time basically swap roles. Out here, where we are, we can move anywhere we want in space, right? Left, right, up, down. But we're all stuck on a one-way trip forward through time. While inside a black hole, it's the opposite. All directions in space now point to only one destination, the singularity at the center. Just like we can't stop ourselves from moving into tomorrow, once you're in, you can't stop yourself from moving toward the center. The singularity stops being a place you can go to and becomes an inevitable moment in your future.
So what does this all mean? Ultimately, black holes are the universe's way of showing us that space and time, they're not this fixed, rigid background we thought they were. They're dynamic, they're malleable, and under the most extreme conditions, they can actually break. These things are the ultimate cosmic laboratories, and they're pushing us, challenging us to find a deeper theory, maybe a theory of quantum gravity, that can finally unlock the ultimate rules of reality.